Stoichiometry, mathematics of chemistry. It is assumed that you can manage formula weights in the basic context. Sum of all the atomic weights equals the formula weight. But it's not assumed that you have a full knowledge of the mole. So we'll start there. And review a couple of points of issue and move on to reactions. Now, a mole is a mass number It is the mass of substance containing 1 Avogadro's number of particles. Well, in the essence of chemistry and in its applications, 1 mole is equal to 1 formula weight. Which is equal to 6.02 times 10 to the 23rd particles of substance. So asked what is the mole weight of such and such, given H2O, this is formula weight to equal 18 grams. We can say that that formula weight is also 1 mole of water. Given H2SO4, formula weight equals 98 grams, sum of the atomic weights. This is equal to 1 mole of H2SO4 molecules. Also, just to review, the subscripts, and that includes the 1 for sulfur, define the multiples of the moles. So this is 2 moles hydrogen, 1 mole of sulfur, and 4 moles oxygen in that structure. So when we talk about H2SO4, 98 grams, we're talking about the entire molecule, but you can extend that to talk about moles of elements in that structure, which is a subscript of that in that formula. Is simply divide by the formula weight. And then moles, 100 grams, multiply by formula weight. So this should be reflexive in your mind. Example, if I ask you what your name is, you don't think about it. You just tell them. So this is what this needs to be. So given 836 grams of H2O, how many moles H2O do you have? Well, that's 836 divided by 18, and that'll give you moles. Because, well, let me put the units in so you can see that. 836 grams in grams per mole. That's 46.4 moles. Now you'll find that in working stoichiometry of reactions, I'm going to tell you convert to moles and solve the problem, and then if they want something else behind that, then you convert back. So in the mass world, it's going from mass to moles divided by formula weight. The other side of that, of course, is moles going to grams. So given 0.0234 mole of oxygen, O2 gas, equals how many grams? Well, formula weight of O2 gas is 2 times 16 of 32 grams per mole, and you have this many moles, so the grams O2 is the product of 0.0234 mole O2 times 32 grams per mole O2. Moles drop out, and you have grams of O2 remaining. Which is 0.7488 grams O2 gas. Okay. What can be calculated from a chemical equation? Most of you have seen these kind of notes before, but enjoy the review. Those that find they need a refresher, please pay close attention here. So we'll start with the equation 3H2 as a gas plus N2 as a gas going to 2NH3 as a gas. And we'll put that across that. And let me put one. Okay, what can you calculate? And you can read it as closely as I can. Moles, mass, particle numbers, gas volumes, energy value, and solution phase reactions. That's what you can get out of a chemical equation. Moles is the first one. Well, when you look at the equation, the coefficients of the balanced equation represent the moles of substance you have. Now, in this form, of course, it's the standard form of the equation, and smallest total number ratio coefficient. So we have 3 moles, 1 mole, and 2 moles. Okay, so you can, once you balance it, you can read the moles straight away from that. Mass is a very important element in this. So how do you get mass out of this? This is called equation mass. And typically that's in grams, and it's the moles times the formula weight. So if I want the gram, the equation mass of hydrogen, I'd have 3 moles times 2 grams per mole, and that of course is equal to 6 grams would be the mass number for that particular one. And then we just bring these on down like that. Here, one mole times 28 grams per mole, 1414, and of course that's 28 grams is the equation mass for nitrogen. And finally 2 moles times 17 grams per mole, 34 grams is your equation mass. Now if you have problems that deal with particle numbers, is relative to Avogadro's number. A capital N, let's subscript O is the common symbology for that. So Avogadro's number, of course, is 6.02 times 10 to the 23rd, as you well know. But if you have to have the number of particles of that substance, it's 3 moles times Avogadro's number in each case, which is particles per mole. And so the outcome is particles. So this would be 1 mole times Avogadro's number. This would be 2 moles times Avogadro's number. Now that's rarely used, almost never in my course. But just to make sure you have been exposed to that idea, there it is. Now, one element from the calculations that is important are gas volumes. Gas volumes are expressed basically out of the equation as what we call molar volumes, and given a symbol Vm, like that. And so the number of moles coefficient times Vm is the number of molar volumes of the equation. So we have 3 Vm, 3 molar volumes of hydrogen, 1 molar volume of nitrogen, and 2 molar volumes of ammonia. Now, the only time you can express V as a numerical value is when you know what the temperature pressure conditions are. And since I mentioned earlier that, say, as written like this, it is assumed that that equation in the lowest whole number ratio is the standard equation. It's at 0 degrees Celsius in 1 atmosphere. At 0 in 1 atmosphere, 1 mole of any gas occupies 22.4 liters. But if you change the temperature or pressure, you no longer have 22.4. So that's the point of just leaving it in VMs as we specified. But if you're going to put a numerical value in there with VM, you have to relate it to whatever the temperature pressure conditions is. And in this case, at STP, VM at STP would be 3 times 22.4 liters, 1 times 22.4 liters, and 2 times 22.4 liters. But it'll be a bigger number if the temperature's higher because gases expand, and a smaller number if we're talking about a temperature less than 0 degrees, minus something or another in Celsius. But from there you can calculate the volumes if necessary in certain problems. I'm going to lose my equation up there, but here, let me do this. Okay, thermochemical equations. Now, out of an equation, you can also calculate energy values if those energy values are attached to the equation in one form of 2, or you can calculate it if you have the thermodynamic properties tables. Let's head this thermochemical equations. Okay, so this particular reaction is an exothermic, so it gives off heat. But some of them will absorb heat. And notice I put the energy on the right side. Well, I can give it to you. H2O as a liquid requires the input of energy to go to gas phase, evaporation, and that kind of thing. These have more energy than the liquid particle. So this one, number 1, is an exothermic. Energy released. And number 2 is endothermic. Energy gained by the system. Now, in order to define endo and exothermic, you have to understand what we mean by system and surroundings. Make a little T-table like this. And we're talking about the flow of heat between the system and surroundings. The system is the object of interest, that in our case, chemical reaction. And surroundings, everything else. So in the basic definition of endo and exothermic, it is with respect to the reaction. if you have a reaction over here and energy is flowing from the reaction to everything else, the surroundings, this is an exothermic reaction. And the important of me saying this is because when you look at the change in energy for the surroundings, it's endothermic. So you're losing energy from one side of the equation table over here and gaining energy in the other side. So when we use the term endo and exo, you want to be sure you kind of in the back of your mind remember that deals with the reaction, not the surroundings. However, let me get the other side of this. If you have a reaction that's receiving energy, this is endo. But it is a unique property or a phenomenon or whatever. When you collect data about energy change or heat flow, you're always measuring this in the surroundings. You never measure the system. In just anything, you never measure the system. It's what the effect of the system on the surroundings. For example, if I have an acid solution and a base solution, say here, and I pour these into a container with a thermometer, I'll observe an increase in temperature. You're observing an increase in temperature. Is the reaction endothermic or exothermic? It's exothermic because what you measured was the solvent water. The temperature change in the solvent and the thermometer, because the reaction in itself is sending energy out to its surroundings. And so when you make a measurement, and you'll do this when we get down the road a little bit on heats of reaction, you have to understand the definitions, what they mean, and when you make a measurement, how to translate that outcome into whatever the system is. It's whatever you measure certainly is endothermic because it's gaining energy, or you wouldn't see a temperature rise. And so, yeah, I see a temperature rising, so I take that as, well, where did the energy come from? It came from the reaction. So I would apply an exothermic terminology to the reaction itself. So that's kind of giving you the physical events that are going on. And there are two ways to write endo and exothermic reactions. Both are used on exams. Let's go back to the ammonia reaction. And you'll see a semicolon, and you'll have a delta H reaction, which is enthalpy or heat of reaction. And on the end, it'll have a number. Delta H equals minus 91. Well, the negative in there indicates the reaction is exothermic. And this is delta H symbology is standard heat of reaction. It's just enthalpy or heat of reaction. Now that's just one way to write the reaction. The second way is to incorporate the number in the equation. And we put that on the product side as and it indicates an exothermic reaction like this. And so you see when I put a plus 91.8 kilojoules. You never put a negative sign when you incorporate the symbology in the equation. It's always plus whatever it is. If you have a negative sign, it's detached from the equation in that form. Both of these have the same meaning. Both are exothermic. For endothermic reactions, you have the same idea, but the delta H is positive or it's incorporated in the reactant side. For example, this is XO. Evaporation of water going from a liquid phase to the gas phase requires input of energy. So we put that detached in this form. Delta H of that reaction is equal to 44 kilojoules in that symbolic format. Notice it doesn't have a symbol. You could put a plus there if you want to, but it still means endothermic. Energy is gained by the system. Or you can incorporate that on the reactant side like this, and that also is an appropriate endothermic reaction. Word equations worksheet. In many problems, you're going to have to translate the nomenclature into chemical equations and then apply the stoichiometry to those. Here they're looking at when aqueous beryllium chloride reacts with an aqueous silver nitrate, aqueous beryllium nitrate and solid silver chloride formula. So what does that look like when you write the reaction for it? Beryllium chloride. All right, beryllium's in group 2, so we will essentially assign a +2 charge to that one. And then chloride's a -1, so I have to put a subscript of 2 on that for the proper ratio of elements. Silver nitrate, I put silver and nitrate together like that, and I know silver is a +1 fixed charge, and then nitrate is a polyion, -1, so that doesn't need any more subscripts than I've already given it. And this will go to, this is a double replacement, see the two salts, AX, BY, and it will go to beryllium nitrate. And the silver chloride. Now, the subscript that I have for chloride on the left does not necessarily mean that the chloride on the right will have the same subscript, because the subscripts on the product side or either side depend on sum of charges equals 0. So that's a very big rule that you need to keep in mind. Also, in metathesis reactions, you do not have any changes in oxidation states. So beryllium, having a +2 charge, has a +2 over here. Nitrates still have its -1, so I need 2 nitrates. So I need to group the nitrates and put a subscript 2. Silver's +1, chloride's -1. So therein is the substances for the reaction. We need 2 here, and we need a 2 right here to balance. And I can tell you the silver nitrate is the driving force of that. That's the part of the happy halides, if you go back and look at the handout. When isopropyl alcohol, that's C3H8O, I'm going to write that a different way. C2 propyl, C3H, we'll go ahead and write it his way. O, burns in oxygen, carbon dioxide and water form. So this is one of those combustion reactions we were referring to, and it's an oxidation reduction, but I have 3 carbons, 8 hydrogens, 8 hydrogen, 2 and 3 is 6, 7, 8, 9, 10. So I can put a 5 right there, and no, take that back. I got a 1 oxygen right there. 2 and 3 is 6, 7, 8, 9, 10. So I have 9. So what I'll do instead of that, I'll put a 9 halves right there. So because the 2 is kind of 9 over 2 times 2, that cancels. And so I have 9 and then 1 is 10. You can use fractions. That's one of the reasons I say leave that element that's by itself to last. And if you need get rid of your fractions, multiply through by 2. So this, well, I'll come down here. I'm going to let y'all do the rest of them anyway. So 2C3H8O plus 9O2 goes to 6CO2 plus 8H2O. So please go through the rest of that. Plus, if you need any more, send me a note and I'll find you, help you find some. Or go online, chemical reaction from nomenclature. She says stoichiometry worksheet. I'm not going to leave it up there like that. I'll work them one-on-one. Okay. Okay, given the following equation, number 1, we got 2C4H10 with 13O2 goes to 8CO2 plus 10 H2O. Now, just as an introduction or a review, show what the following molar ratios should be for the C4H10 and oxygen. So you're looking at this against that. Well, that's a 2 to 13 molar ratio. And so, well, I should have written that a little bit differently for you. 2C4H10 to 13 moles of O2. Simple, just read oxygen and CO2. So we're looking at oxygen and the CO2. That's the 13.8. So that's 13 moles O2 to 8 moles CO2. And that relation O2 and water. That's an 8, 13 to 10, 13 moles, and so forth. So just getting some basic concepts reviewed and refreshed. And when you look at an equation, there is a mole-mole relationship in equations once it is balanced. Okay, number 2 in here, given the equation 2KClO3, that's 2KCl, decomp reaction, plus 3O2. He wants to know how many moles of O2 can be produced by letting 12 moles of potassium chlorate react. So we have 12 moles of KCl, and the question is how many moles of O2 are generated. A couple of things you can do. One is your ratio and proportion, and that is 2 is to 12 equals 3 is to x. Solve for x is 3 times 12 over 2, and that's moles of O2 formed. Or you can just simply look at this. All right, you got KClO3. What's the coefficient? 2. What's the coefficient of O2? 3. 3 is a bigger number than 2, right? Okay? So you would take the ratio of those numbers times whatever the 12 moles is, because you need to scale this up to a bigger number, because you need to go 3 halves of 12. You don't want to go 2/3. That'll make a smaller number than 12 because you're going to a larger side. So the moles O2 would be 3/2 of 12 moles. Well, both of them bear out in the calculation, whatever that comes out, and you punch it in yourself. Okay, the question is, how many grams of potassium chloride will be produced from 2.5 grams of potassium in an excess of chlorine gas? When a reaction is given such that one of the components is in excess, then it means this one will be the dominant component. Or another way to look at it, it is the limiting reagent. Or reactants, to be more accurate. It is the component of the reaction which goes away first and the reaction stops. Very important that you understand that. Now, in working problems like this, my philosophy, many of you have come here with different methods. That's fine if it gives you the right answer. But the most consistent method that I've found that people can remember long term is use the mole concept. Convert your values to moles. Solve the problem by mole ratios, and if they want something else, which is grams in this one, convert it at the end by multiplying by formula weight. So 2.5 grams in potassium is 39 grams per mole. So 2.5 grams over 39 grams per mole is 0.064 mole of the potassium. Now 2 moles gives 2 moles. Well, since the coefficients are identical, then the yield of this will be 0.064 mole. This is a 1-to-1 mole ratio. Okay, so the grams now of the KCl formed is equal to 0.064 mole times formula weight of the KCl. And that's 39.35. I get 74, so that's 0.064 mole times 74 grams per mole. .774 grams KCl. See how I did that? Okay. Stop me if you need to. I'm going to splash through these things like a rocket. But the idea here is to convert the given data to moles, solve the ratio, and at the end convert back to whatever they want. We'll work that, and then the second half of this. Given the following equation, you got copper and silver nitrate in a single replacement reaction. Going to your copper nitrate plus a couple of silver, moles of silver coming out of solution, like that. How many moles of copper are needed to react with 3.5 moles of silver nitrate? So what are we looking at? 2 to 1. So the number of moles of copper will be less than the moles of silver nitrate given. It's a smaller number over here. It's a 1. Okay? So if I take the ratio of 1 and 2 times whatever I'm given to generate a smaller number, then I'll have the right answer. Moles copper should be less than moles of silver nitrate, because the coefficients show that. And so the moles of copper is equal to 1/2 of 3.5 mole of whatever the silver nitrate, whatever that is. I don't trust my brain. 1.75. See what I did on that? You see how I'm kind of looking at the coefficients of the standard equation and says, okay, if I'm given this much, should the number be smaller than that given or bigger than that given? Well, in this case, it needs to be smaller by the ratio that will give me a smaller number. You certainly don't want to multiply 2 over 1 times 3.5. That's not going to give you a smaller number. See the point? Everybody good? All right. The next part of that, if 89.5 grams of silver were produced, how many grams of copper reacted? So we'll have in part B of that, I'll rewrite the equation for academic reasons. So 89.5 grams. How many grams of copper were used? Convert to moles and solve it, and then times the formula weight of copper at the end of that. Well, it's a 2-to-1 ratio. So once I get to moles, I cut it in half times the formula weight. Okay. Silver, 207, I think. That's cool. 107. Okay. Divided by 107.9. .829 mole of silver was produced. How much copper? Well, it's a 1-to-2 ratio, and copper will be smaller number of moles than silver, so I want to use 1/2 on the moles of silver. Like that. Now, the formula weight of copper is 58.9. No, that's cobalt. Let's see. Oh, 63.5. And I have 26.4. Yes. So if you can work through your moles, I think it's much easier than trying to do dimensional analysis. If you like it, fine. All you're going to have to do is pick A, B, C, D anyway. So whatever. And so it's not a big deal. So we're looking at this worksheet, if you have it available. Okay, you'll get that in front of you. Sodium chloride can be prepared by the reaction of sodium and chlorine gas. If 6.7 moles of sodium react with 3.2 moles of Cl2, what's the limiting reagent? How many moles of sodium chloride are produced, and how much of the excess remains? All right, so we need sodium chloride, can be prepared by the reaction sodium solid, basic standard state, plus chlorine, which in its basic standard state looks like that. We'll go to sodium chloride. In its standard state, it's a solid like that. So I'm going to need a 2 and a 2 to balance that equation. If 6.7 moles of sodium is mixed with 3.2 moles of chlorine, what's the limiting reactant in that? The simplest way that I found, and this is just a technique, but divide moles by the respective coefficient. The smaller value is the limiting reagent. If you've never heard that before, I'll say it again. Divide the mole values by the respective coefficient. So we divide by 2 for the sodium and 1 here. So this will give you relative numbers. There is reason, but you don't need that right now. .35 and 3.20. So this is a smaller number. And therefore, is the limiting reagent is the chlorine. So the other hidden meaning is that all of the chlorine is going to be used up, but you will have some sodium in excess. It will be the one that won't be you won't use all the 6.7 moles. Now, after doing that, work the problem using the limiting reagent mole value. All right, this is finished. Once you determine the limiting reagent, work the problem mole values, not the values resulting from dividing by coefficients. Everybody clear on that? So you got to go back up and work from the mole values. So when you do that, this being the limiting reagent, the ratio is a 2-to-1. So when you want to predict the moles of sodium chloride, is based upon the chlorine, the 3.2. And the number needs to be larger. By how much? 2 times. So you get 2 times 3.20 moles of NaCl, and that's 6.4 mole of NaCl produced. That's all you're going to get, because when that 6.4 is produced, this is gone now. Now you may use up some of the sodium, but you're not going to use all of it. How much of the sodium will you actually use? Well, it's a 2-to reaction ratio. Well, the yield is 6.4 right here, or you can use it. That's how much of the sodium chloride you produced. So if you put 6.4, that means you've got to use 6.4 moles of the sodium also. So 6.70 mole available in a used. I should have done that. let me write that a different way. Na available is equal to 6.70 moles, but you used 6.40 moles. So sodium in excess, there's a difference in those two. So in working problems, you'll run into that many times. Now where it gets kind of tricky, and that's why I'm emphasizing this, is when you get the solution data, where you have to convert solution data to moles and then find out which one is the limiting reagent in some acid-base titrations type systems. Theoretical yield is value from calculation. Actual or lab yield is the reality factor. That's the real amount formed. If you want to calculate a percent yield, it is given by the actual yield over theoretical yield times 100%. Okay, so let's see how this works out. Nitrogen gas can be prepared by passing gaseous ammonia over solid copper oxide at a high temperature. The other products of the reaction are solid copper and water vapor. If a sample contains 18.1 grams of ammonia, is reacted with 90.4 grams of copper oxide, what's the limiting reagent? How many grams of nitrogen be formed? If only 8.2 grams of nitrogen are actually formed, what's the percent yield? So you can read as well as I can. Okay, so let's get our equation written first. Nitrogen gas can be prepared by passing gaseous ammonia. And we'll start with NH3 gas over copper oxide. At high temperatures to produce copper and water vapor. Oh, forgot plus N2 gas. We got to put the nitrogen in there, don't we? I can write that out a little better so we can may have a more usable form. Let me see if I can spread that out. NH3 is copper oxide, goes to copper plus H2O plus now N2 gas. So, yeah, that'll work a little better for us right there. All right, let's get our data in. See if we can put some numbers in here. If the sample contains 18.1 grams of ammonia, react with 90.4 grams of copper oxide, and they want to know how many grams of the ammonia is performed, and the actual yield is 8.2 grams. Put that back down a little bit. So, what's the rule? What's the first thing I need to do? Anybody? Invert the moles, right? How do I do that? Divide by formula weight, right? Everybody good? All right, so this one's divided by what? 17. 14, 50, 60, 17 grams per mole. And copper oxide, 63 and 16. Yeah, 63 and a half plus 16. Ah. 79.5. So that's 1.14 mole. 18.1 over 17. 1.07. Everybody still with me? Okay. So they want to know what the yield of copper is. So who's the limiting reagent? Are we balanced? Let's see if we're balanced. Got to have a 2 there. We'll save that into last. And hydrogen's got to be 6. So we got 2 and 2. 2 and 3 is 6. 6. And a 3 and a 3. Does that look like balance? 2 nitrogens. 2 nitrogens. 2 and 3 is 6 hydrogens. 2 and 3 is 6 hydrogens. Got 3 oxygens. 3 oxygens. 3 copper. There we go. Everybody good? All right. So now, given this, we want to divide this one by 2 and this one by 3. So that's divided by 2. That's a 0.53. And 1.14 divided by 3, 0.38. That's the limiting reagent. It's the smaller of 2 numbers. Everybody still with me? Very good. Okay. So we're going to base this on the copper oxide moles. So 1.14 goes 3 to 1. Okay? Is the number that I'm supposed to get over here bigger or smaller? Y'all know the difference between big and small? Somebody say, smaller or bigger? I got 1.14 here. What's this number supposed to be? Bigger or smaller than the 1.14? So if I'm going from 3 to 1, I've got to reduce that. You don't want to multiply it by 3, so it's 1/3 of 1.14 mole. That's 0.38 mole generated. Well, 14 is 28, so times 28 grams per mole. $10.64. This is the theoretical yield. So the percent yield is theoretical, actual over theoretical, times 100%. The actual is 8.2 that's given in the problem over 10.64 times 100%. So we've got a 77% yield.